Hey guys, in this video we're going to be looking at some advanced techniques for integration by U-substitution. So in order to be able to follow along with this video, you're going to need to be familiar with the basics of U-substitution. So if you're not, go ahead and check out the previous video where I went over the basics of U-sub and just like the standard procedure. And once you're comfortable with that, we can go on to some more advanced techniques. Okay, so the first one, sometimes when converting from the X world to the U world, the du will not line up with all of the outside stuff, and we have extra x's floating around. These can be converted to u's using our U equation. So example 1, we're going to evaluate the integral 1 over 1 plus the square root of x dx. So if we let U equal, it's usually when we have a rational function, either the entire numerator or the entire denominator. So we'll say U is 1 plus root x, or 1 plus x to the power 1/2. That means our du would be 1/2 x to the negative 1/2 dx. Or, in other words, 1 over 2 root x dx. Okay, now let's go ahead and make the substitution. So this becomes the integral of 1 over u. And, whoops, we need to do one more step here. Let's go ahead and take this equation, du equals 1 over 2 root x dx, and solve for dx by multiplying both sides by 2 root x. So we get 2 root x du equals dx. So we're going to make this substitution for dx here. So 2 root x. Okay, so everything didn't line up perfectly. We have this extra root x floating around. The 2 is not a problem. We can just pull that outside of the integration symbol. But the first trick is to go back to our U equation. So we're going to go back up here, and we're going to solve for x in terms of U. Now, in this case, we want a root x. Okay, so we actually don't have to go all the way and solve for x. We can just solve for the square root of x. All we have to do is subtract 1 from both sides. So we get the square root of x equals u minus 1. And now let's go ahead and make that substitution, and at the same time just pull the 2 outside of the integration symbol. So now we have 2 times the integral of the square root of x is u minus 1. We could go ahead and put that in the numerator of the fraction. U minus 1 over u. Now let's go ahead and break that into 2 separate fractions. We have 2 integral u over u is just 1 minus 1 over u u. Okay, now we can go ahead and take the antiderivative. So we're going to have 2. The antiderivative of 1 in terms of u is going to be u. And the antiderivative of 1 over u is ln absolute value of u. And because this is an indefinite integral, we add plus c. Okay, now let's go ahead and distribute the 2. So we're going to have 2u minus 2 ln absolute value of u plus c. Now, because our initial question was in terms of x, we have to go back to the x world. Our answer needs to be in terms of x. So we go back up here. U is 1 plus the square root of x, or we can reverse that and say the square root of x plus 1. We have 2 square root of x plus 1 minus 2 ln absolute value, square root of x plus 1 plus c. Okay, now I'm running out of space here, so I'm going to come all the way over here. And let's go ahead and distribute that first 2. We have 2 root x plus 2 minus 2 ln. And let's think about the absolute value bars for a second and whether or not we actually need them. So we have a square root of x, whatever x is, plus 1. Well, a square root cannot be negative. So the square root of any number has to be either 0 or positive, and then we're adding 1 to that. So what's in the absolute value bars is always going to be positive, assuming the x is in our domain. Okay, so we do not need the absolute value bars, so we can drop them. So ln root x plus 1 plus c. Now, you may think that's the final answer, but you never want to have a constant and a parameter in your final answer. Okay, because c is just a random number or an arbitrary number between negative infinity to infinity. It's any real number. And if you take a random number from negative infinity to infinity and you add 2 to that, you still get a random number from negative infinity to infinity. So the c plus 2, we could just combine into just c. So our final answer is going to be 2 root x minus 2 ln root x plus 1 plus c. Now, if you want to do things properly and completely 100% technically correct, what you would actually do is you would rename one of these c's. Okay, this c is different than this c. So if we call this c1 instead of just c, and then we say let c equal c1 plus 2, now we have this 2 plus c1, and they combine to equal this c here. Okay, now in practice, we do this a lot when we're working with indefinite integrals, and sometimes you would need a c sub 1, a c2, a c3, a c4. And so in practice, it's just easier to just call it c every time. And each time you have a parameter c and you add a number to it, you still get c. You multiply it by a number, you still get c. It's a different c, but in practice, we don't even bother with the subscripts. Okay, let's move on to the next example. And we have a hint at the top. When an integrand involves trig functions, sometimes it appears that the U-sub method will not work, but changing the form using the trig identities could reveal a U-sub solution. The first thing to try is to change everything to be in terms of sine and cosine. So here we have a very simple integral, just the integral of tangent x dx. And it doesn't look like a problem where you would use a U-substitution. In fact, a lot of the cheat sheets will actually give you the integral, what it evaluates to in the integration table. So here it is right here. But this is kind of a cheating way to do it, because not many people know off the top of their head that the derivative of ln absolute value of secant u is tangent u. And usually you would only use the table for common known derivatives. So not many people commonly know the derivative of ln of absolute of secant u. So the more proper way to do this one is to do a U-substitution. And let's take the advice of the instructions or the hint at the top, and let's start by putting everything in terms of sine and cosine. So tangent is sine x over cosine x. So this integral is equivalent to the problem. Now this looks more like something that can be solved using a U-substitution. Now, if we make our u sine x, the derivative is cosine x, And du would be cosine x dx, which seems to line up, except that it doesn't. Because cosine x dx, the cosine is in the numerator, and our cosine is in the denominator. So it doesn't really work. On the other hand, if we make our u cosine x, then our du would be negative sine x dx. And that lines up except for the negative sign, but a negative sign is just multiplying by -1. It's just a constant. And remember, we can manipulate the constant however we want. We can just pull the negative sign outside of the integration symbol. So let's do it that way. So u equals cos x du equals negative sine x dx. And dx equals, so we're going to divide by negative sign. You could write it as negative cosecant, or you could write it as -1 over sine. I think in this case it's going to work better if we write it as -1 over sine. Okay, now let's make our substitutions. We have the integral of, okay, so u is cos x, so we have sine x over u. And then dx is -1 over sine x. Sorry, one of these should say du. Sorry about that. Dx is -1 over sine x du. Okay, the sine x's cancel. We pull the negative outside of the integration symbol. So now we have negative integral 1 over u du. And the antiderivative of 1 over u is ln, absolute value of u. It's an indefinite integral, so we do plus c. And now we have negative ln, absolute value, cos x plus c. Now that didn't quite match what they gave us in the integration table, did it? Let's see. The integral of tan u, so they have no negative sign, and they have secant u inside the absolute value bars. Now I'm pretty sure that's going to be the same answer. But the question is why? Let's go ahead and check Desmos just to verify that it's the same answer. Because the reason why gets into more trig, and it's not really appropriate for this video. So let's just make sure we have the correct answer. ln secant x . What's wrong here? Use parentheses around the argument of ln. And then negative ln of absolute of cos x. And yes, right? Let's see. Yeah, so it's the exact same function. There's just some kind of trig identity you can use to convert this into this. But the point is we have the correct answer, so we're good to go. Okay, let's go to the next example. So we have the integral of the natural log of tangent x over sine x cos x dx. Okay, so we have a lot of choices for what to make our u. I I feel like when you have the argument of a function, like a natural log function or a trig function or an exponential function, that usually takes weight over like using the entire numerator or the entire denominator. So I'm guessing the best thing to make our u is tangent x. And you might be wondering, well, how do I know that? I don't have the same experience. I would have no idea what to make the u. Well, use the guidelines. With the guidelines, there's a few choices. You could do ln of tangent x, the entire numerator. You could do sine x, cos x, the entire denominator. You could just do tan x like I did. And if it doesn't end up working out, then just assume that you used the wrong u and go back and try a different one. We actually might see that in one of these examples coming up here. But let's go ahead and try it with u equals tangent x. That would make our du equal to secant squared x dx. And then to solve for dx, we divide both sides by secant squared. 1 over secant squared is cosine squared. Let's make our substitutions. So now we have the integral of ln u over sine x cos x times cosine squared x du all right. So one of these cosines will cancel. Okay. So now we have integral. And we want to be a little bit careful how we write this. We have ln u, and then we have cosine over sine. And if you remember back to the first example, we wanted to use our u equation to kind of take care of the outside stuff that wasn't accounted for. Okay, so our u is equal to tan x. So how can we make a substitution with tan x that could take care of that cosine x over sine x? Well, cosine x over sine x is cotangent of x. And cotangent of x is 1 over tangent of x. So let's do this in 2 steps so it's more clear. We'll have ln u, and then cosine x over sine x, let's write that as cotangent x du. And now cotangent x is equal to 1 over tangent x, and tangent x is equal to u. So we can write this as ln u times 1 over u du. Well, now what? We still don't have an integrand that looks like a known derivative. I don't think you're going to find this in the integration table. However, if I'm looking at it, to me it's looking like an integral that could be solved using a u-sub. We've already done a u-sub, but as you saw in the previous video, we could do multiple u-subs. Because the derivative of ln u is 1 over u, that should match up perfectly with the v in this case. So we've already used u, let's use v, and set that equal to ln u. And the reason I chose that for the v is then the dv would be 1 over u du, which lines up perfectly, 1 over u du. And then let's go ahead and solve for du equals u dv. Now let's make the substitutions. We have the integral of v. So ln u is equal to v, and then we have 1 over u. And then we have our du, which is equal to u dv. And the 1 over u and the u cancel. So now we have the very simple integral of v dv. I'm going to come up here so there's more space. We can evaluate that, so I don't need the integration symbol anymore. Just use the power rule, so we're going to have v squared over 2. And we're going to have to first back substitute the u and then back substitute the x. So v is ln u. So we're going to have ln u squared over 2 plus c. And now our u is tangent of x. So we have ln of tangent of x squared over 2 plus c. That's our final answer. Let me double check to make sure that's correct here. Ln of tangent of x quantity squared over 2 plus c. Yeah, we got it. Okay, so we had to combine a few techniques here. We had to deal with manipulating the trig ratios into different trig ratios in order to get it to work how we wanted. We needed to do the U-substitution more than once. And we needed to use our U equation in order to kind of take care of the outside stuff that didn't line up with the initial du. Okay, example 4, evaluate the integral. We have x over 1 plus x to the 4th. Now, the most logical choice for our u should be 1 plus x to the 4th. So let's try that. U equals 1 plus x to the 4th. So then our du would be 4x cubed dx. And our dx would be 1 over 4x cubed du. Okay, let's make our substitution. So now we have the integral of x over u, and then dx is 1 over 4x cubed du. One of those x's will cancel, so this goes away. This becomes a 2. The 1/4 we can pull outside of the integration symbol. So we have 1/4 integral of 1 over ux squared. So we have this extra x squared hanging out. Can we use our u equation to solve for x squared and get this into something that we can actually integrate? Let's see. I'm going to take this equation. We're going to come down here. Let's start by subtracting 1. So x to the 4th equals u minus 1. And we'll take the square root of both sides. So we end up with x squared equals square root of u minus 1. So that gives us 1/4 the integral 1 over u square root u minus 1 du. Now, I'm not really seeing a way to go from here. It doesn't seem like this method is working out. which could indicate that we chose the wrong u. Now, we did in fact choose the wrong u. There are two hints, two things you might recognize in order to know what u to choose. Okay, the first thing that we talked about in the previous video is usually when you have two polynomials, you want one polynomial to be exactly 1 degree less than the other. So we have the u as a degree 4 polynomial, and the numerator just x as a degree 1 polynomial, which isn't ideal in a u-sub. Usually you want the 1 to be exactly 1 degree less than the larger one. The other thing to recognize here, if I go to the integration table, we have a bunch of known integrals. It's not highlighting the way I'd want it, but if you look at this left side over here, okay, and we don't have a square root, so we want to look for the one that doesn't have the square root. But if you're familiar with the integration table, I encourage you to you don't have to memorize this completely, but if you're just kind of familiar with it, you'll realize that I think there's something in the integration table that kind of looks like this: 1 over a squared plus u squared. Okay, so let's see if we can combine those two things and see if we can pick a better u. So I'm going to go ahead and erase all of this. Oh, let's go ahead and see if this will make it easier. There we go. Okay. So, did you figure out what we should make our u? Based on what we saw in the integration table and the fact that we usually want our u to be 1 degree higher than the other polynomial, let's make our u equal to x squared. And then our du becomes 2x dx, and dx is 1 over 2x du. Let's make the substitutions and see what we get. So now we have the integral of x over 1 plus x to the 4th would be u squared, and then dx is 1 over 2x du. The x's cancel. We can pull 1/2 to the outside of the integral. So we have 1/2 the integral 1 over 1 plus u squared u. And let's just double check the integration table. This says 1 over a squared plus u squared. So the only difference between this and what we have, instead of a squared, we have just 1. So we know that a equals 1. And let's go ahead and plug that into the formula. So we're going to have 1/2. So we have u is just u and a is 1. So we use the formula. We get 1 over a is just 1, so 1 over 1 is just 1. We don't need to write that. Arctan of u over a, so just u, plus c. So we have arctan of u plus c. So 1/2. Oh, we don't really need the parenthesis, do we? One-half arctan of x squared plus c. Okay, moving on to the next example. This one says, sometimes a U-substitution will reveal itself if you complete the square of a quadratic expression. So we have a quadratic expression inside a square root symbol in the denominator, negative 8x minus x squared. Let's go ahead and complete the square, and based on the hint it's giving us, and just see what happens. So we're going to have negative x squared plus 8x. So I'm just changing the order. I don't want any coefficient in front of the x squared, so I factor out the negative. Okay. In order to complete the square here, we take half of the negative 8x, or half of the negative 8, I should say, which is negative 4, and then we square it, and we get plus 14, or plus 16, excuse me. Okay, so this part inside the parentheses is equivalent to a perfect square trinomial. It would be x minus 4 squared. If you take x minus 4 squared and FOIL it out, you get x squared minus 8x plus 16. Now, we can't just add this plus 16 willy-nilly. We can only add 0. So if we add 16, we have to subtract 16. But in this case, we actually subtracted 16 because that negative outside the parentheses applies to the 16. So if we subtracted 16, we have to add 16. Okay, 16. And now I want to rewrite this. We'll put the 16 in front, minus, and we'll change this to the squared form. So x minus 4. Okay, now let's rewrite our integral. We have the integral. Let's go ahead and pull that 3 to the outside. 1 over square root 16 minus x minus 4 squared. Now, let's go back to the integration table. We have, in the same section, we have this one that has the square root in the denominator. So we want to make the denominator look like the square root of a squared minus u squared, and then we can use this formula from the table. Okay, so that means our a squared would have to be 16. So a would be 4. And our u squared would have to be x minus 4 squared. So u is x minus 4. Then our du is just equal to dx if we take the derivative there. Okay. So now we have 3 integral 1 over square root. I'm going to write this 16 as 4 squared so it's easier to see, minus u squared, and dx is just equal to du. So now we have the integrand in this format which matches what we have in the table exactly. So we're going to have 3, and let's apply the formula from the table. So we have arc sine of u over a, and a is 4, so arc sine of u over 4 plus c. 3 arc sine. Let's go ahead and do 2 steps in one. U is x minus 4. So we'll have x minus 4 over 4 plus c. Let's get rid of that first parenthesis. And there's our answer. Okay, we have one last problem. Evaluate the integral x cubed square root x squared plus 1 dx. Okay, the most obvious choice for our u seems to be x squared plus 1. That would make our du 2x dx. That makes our dx 1 over 2x du. Let's go ahead and make the substitutions. So we have integral of x cubed root u times 1 over 2x u. Okay, one of these x's will cancel. And the 1/2 we can pull outside the integration symbol. So now we have 1/2 integral x squared square root of u du. Okay, and let's see if we can use our definition of the u to get that x squared to be in terms of u. Well, u is simply x squared plus 1, so then x squared would be u minus 1. So let's go ahead and make that substitution. So now we have 1/2 integral u minus 1. I'm going to say this is u to the 1/2 to make it easier. du. So we have 1/2. Let's go ahead and distribute here. The integral u to the 1 times u to the 1/2 is going to be u to the 3/2 minus u to the 1/2. And now we can simply use the power rule. We have 1/2. So we add 1 and then divide. So 3/2 plus 1 is 5/2. And divide by 5/2 is the same as multiply by 2/5. We're going to get 2/5 u 5/2 minus 1/2, add 1, we get 3/2 u to the 3/2, and then we divide by 3/2, which is the same as multiply by 2/3. Plus c. And we can go ahead and substitute the x squared plus 1 back in for the u. We can distribute the 1/2, so 1/2 times 2/5, the 2's cancel, we get 1/5. And then x squared plus 1 to the 5/2 minus the 2's cancel again, so we're going to get 1/3. U is x squared plus 1 to the 3/2 plus c. Now this can be the final answer. I'll give you probably a slightly better way to write it. So we have some common factors here, right? We have a GCF. We got a 1/5 and a 1/3, and then we have an x squared plus 1 to the 5/2 and an x squared plus 1 to the 3/2. So the GCF between 1/5 and 1/3 is 1/15. So we can factor out a 1/15, and we have x squared plus 1 to the 5/2 and x squared plus 1 to the 3/2. So we could factor out an x squared plus 1 to the 3/2. Okay, if we factor that out from this first term, okay, 1/15 times what is going to be 1/5? That's going to be 3. And then how many x squared plus 1's do we have left? Well, we had 5/2. We factored out 3/2, so we have 2/2 left, which is 1. So we have 1 x squared plus 1 left. Minus, and then when we factored the GC out of this, what's left? Well, 1/15 times what is 1/3? That's going to be 5. And we factored out the entire x squared plus 1 to the 3/2, so that's gone. So it's just 5. C, and we can clean that up a bit. 1/15 x squared plus 1 to the 3/2. 3 times x squared is 3x squared. 3 times 1 is 3, and then we subtract 5, we get minus 2. So that is also a valid answer. It's a little bit subjective. which is nicer. I think the second one in blue is a little bit cleaner. Okay, that's it for the video. Thank you for watching and see you next time.